I'm going to talk a little bit more, maybe to amplify a little bit of what Sean talked about as far as the scale of implementation. I'm going to show a little bit of data on how some of these practices perform as we think about getting them on the landscape. Again, as Sean talked about, I think one of the real positive things that's come out of states doing these science assessments is a better understanding that the primary reason for our high nitrate levels is not fertilizer mismanagement. And I think as we think about the weather variability that we have, that's a huge driver. And so I know for some in the back, this is a number of lines on here, but this is from 25 years of data where we applied 150 to 160 pounds of nitrogen to corn in a corn-soybean rotation. These are on replicated plots near Gilmore City, Iowa. And so you can see that green line is the annual drainage. And you can see 1993, a lot of drainage. We got a lot of precip, right? 1994, you'll see it's down to less than an inch of drainage. So that year-to-year variability is very big. The blue line, or the blue dots and line, it's the flow-weighted annual nitrate concentration from that combined corn-soybean system. What we see in those years around 92, 93, 94, 95, kind of in the period during and right after those high rainfall event, high drainage, we saw kind of flush the system out, fairly low nitrate concentration. But then we look at, toward the end of this slide, 2013. We had flow-weighted nitrate concentrations above 20 parts per million of nitrate-nitrogen, okay, about double the drinking water standard. Same management, it's just in that case, wet spring, but was preceded by a drought condition. So if we're going to manage this in field, there would be a challenge in knowing that we're going to have a drought and seeing low nitrogen utilization and being able to plan for that. I think it just illustrates how weather is still a big driver in this. But our nitrogen application rate does influence what we see in nitrate coming out of our tile lines. The line on there relates flow-weighted annual nitrate concentration from a corn-soybean rotation to, on the x-axis, the nitrogen application rate to corn. And what we see is that as we increase, if at higher application rates, we see more nitrate coming out of the system. Right now, from our best estimates in the science assessment, the average nitrogen application rate to corn-following beans is about 150. The maximum return to nitrogen for a ratio 0.1 for the price of nitrogen to the price of corn is about 140. So even if we reduce from 150 to 140 on average, that's only about a 9 to 10% reduction statewide. Now, if in certain operations we're closer to 200 and we move down to 140, we'd have a much bigger reduction in that case. One of the things we don't know that distribution. We estimated from fertilizer sales and animal numbers that 150 value, but we don't know the distribution around that, which we think is critical. Another factor on this curve is that you'll notice even when we put no nitrogen on in our corn-soybean rotation, we still see about 7 parts per million nitrate-nitrogen coming out the tile line. So if we went from 150 to 0, we get about our 40 to 50% reduction. That's kind of the maximum we could expect with infield nutrient management. That'd be the most aggressive nutrient management that we would do. Wouldn't be what we'd want to do, and there could be downside because ultimately it could have a negative impact on our soil quality. But I think it illustrates the challenge in just meeting these goals with infield nutrient management or nitrogen management. Okay. A question that I often get is, how does the nitrate leaching from sites where we apply liquid swine manure compare to where we apply commercial fertilizer? And we have some data on that. We're continuing some of that work. But this is from some published work from Gilmore City. And so we had fall ammonia, spring ammonia, fall manure, spring manure, and we applied ammonia at 150 or 225. Now, the manure was applied at 200 pounds of nitrogen per acre, okay, in the total nitrogen there. Okay, so if you were just to look at the fall manure, spring manure, or fall ammonia 150, spring ammonia 150, compared to the fall manure and spring manure, you'd say there's higher nitrate concentrations. But that's because there was more nitrogen applied. So if we look at that 150 for ammonia and the 225 for ammonia, that fall manure is right in line with that. So you can think about that manure was 200, the ammonia was 150 and 225, and that manure falls right in line. From our work with the nutrient reduction strategy, we would say if we apply our manure, liquid swine manure in this case, at similar nitrogen application rates as commercial fertilizer, we see similar nitrate loss from our systems. I think that's critical. And we all know some of the benefits that you see from your soil and from productivity in using that manure. Okay, the underlying processes, and this kind of gets at what Sean talked about as well. This is another slide from Dr. Mike Castellano at Iowa State University. And that red line illustrates the rate of soil nitrate production from that native soil organic matter. So that 100 to 200 pounds that Sean mentioned, that's kind of how the rate at which that's produced during the season. That green line is the estimated rate of corn or soybean nitrate uptake. And if you look at that red line compared to that green line, we see one of the reasons why we have some of the problems that we do. When do we see that gray area or the mismatch? It tends to be during that vulnerable leaching period in the spring of the year. Or even in the last few years, in the winter or in the fall, in November and December. At our drainage sites this year, we collected samples all the way up to Christmas, where normally we're done sampling by Thanksgiving for sure. So, as we look at this, now we can think about, would the green line, as Sean talked about with land use change over the last 50, 75 years, if we think about that red line, that probably hasn't changed. But that green line has probably changed as we've gone to just primarily a corn-soybean rotation. If we had some small grains or some perennials in the system, we probably moved that green line a little bit more in line with the red curve that we see there. Okay, but one of the things we can do in the corn-soybean rotation, as Sean talked about, is cover crops. We'll hear more about that from our farmer speakers, but this is just a couple slides at a couple of our research sites, one near Ames, one near Gilmore City. Gilmore City is up in Pocahontas County, so a little bit more north along Highway 3. What we would hope is that cover crop in the spring and the fall can take up some of that nitrate, reducing that gray area between the red line and the green line. What we've seen from 9 years of data near Gilmore City is about a 25% reduction in the nitrate-nitrogen concentration that we see in the tile line where we're growing a winter cereal rye cover crop after both corn and beans. Now, I would say that this is kind of at the low end of the reduction that we could expect. We have drilled this rye after corn or soybean harvest, so it goes in between the 15th to the 25th of October. We don't get a lot of growth in the fall of the year up at that location. So as we think about it, I think this is toward the low end of what we could expect, but even in that case, we see about a 25% reduction. I think there's a lot of work to be done to look at how we can seed this to maximize the biomass growth, or optimize the biomass growth. Now here's a little data from Ames. Again, we have a cover crop in here, winter cereal rye. I just draw your attention to that kind of middle section there. That's the nitrate concentration from 4 years for these different systems. This is commercial fertilizer, but the black bar is corn in a corn-soybean rotation. Red is soybean in a corn-soybean rotation. Green is continuous corn. Blue, continuous corn with winter cereal rye cover crop. And then fertilized prairie and fertilized prairie. Guess few things to note here. One, we see similar concentration in the soybean year as in the corn year. We see slightly higher nitrate concentrations in this case under continuous corn, but considering we're applying nitrogen both years, 2 years. So about, in that case, it's probably about almost 400 pounds of nitrogen over 2 years versus 150. It's maybe not as much as one would think. We see about a 50% reduction in nitrate where we had that cover crop. But then if we go to a perennial, thinking back to that red line and green line on some of the previous graphs, where we're probably a little more matched in the timing, we see very low nitrate coming out of that system where we have prairie or that small kind of turquoise or teal, whatever. That one is where we've applied 50 or 75 pounds of nitrogen per acre per year to maximize above ground biomass of the prairie. Okay, so what can we do? The nutrient reduction strategy talks about nitrogen management, land use, and edge of field practices. You can all get online and see this, but we looked at what literature is out there for the region, for the impact of timing, source, rate, and inhibitor products on reducing nitrate loss and on subsequent corn yield impacts. I think the 4 R's under the nitrogen management are where we need to start, because many of these not only benefit water quality but may have a crop yield benefit, or at least very little decrease on crop yield. And if we're reducing input price or input costs on a nitrogen application rate, we may see greater profit from our system. But one of the things you'll notice if you look at that, the average, so the percent nitrate reduction for the average, what you're going to see is that all of these practices, on average, reduce nitrate concentration 10% or less. And what was our goal again? About a 45%. Okay, so it kind of illustrates the challenge with just meeting this with infield nitrogen management. As we go to some of our infield or land use practices, you'll start to see greater percent reduction for those practices. Cover crops 30%. If we go down to a diverse rotation, maybe a couple years of alfalfa in the rotation, we're at a 40% reduction. But then some of our edge of field practices, Sean kind of talked about our drainage water management, our wetlands, bioreactors, saturated buffers. So you've seen this slide, but just again, subsurface drainage bioreactor, a wood chip trench. We're primarily using wood chips presently as a carbon source for the microbes. We're converting that nitrate to nitrogen gas using the natural denitrification process to our benefit. The saturated buffer, you know, we've all driven around Iowa and we see many buffers in there. The nitrate is primarily transported in subsurface flow, and in those tile drain landscapes, that tile line is running right under the buffer. We're not getting much benefit. Let's put in a control structure, try to have shallow groundwater flow through that buffer zone. The nitrate removal wetlands, in this case, we may be taking 1 to 2% of a watershed area. We might have a 1,000-acre watershed. We take 1 to 2% at the base of that watershed, put it into a wetland, and then maybe some buffer area around there. Might be able to reduce nitrate export from that watershed by 50%. And if we look at this, at least to some, this would provide other benefits on the landscape. Waterfowl, wildlife habitat, maybe in the buffer around there, some pollinator and monarch habitat as well. So perhaps multiple benefits. Okay, so what might it take? And Sean talked a little bit about this. This is just one example scenario, in no way a recommendation, but an example scenario to reach the nitrate reduction goal, where the scenario includes looking at our application rate, reducing that slightly to the MRTN. 60% of all acres that are in corn bean or continuous corn have a cover crop. 27% of all ag land treated with a wetland, and 60% of all subsurface drained land with a bioreactor. As we look at that, the amount of treated acres under that scenario, you know, we have about 18 million acres treated where we're reducing N rate, about 12 to 13 million acres where we have a cover crop. We have about 7 million acres treated by wetlands. So that's not 7 million acres of wetlands, 7 million acres treated by the wetland, and 6 to 7 million acres treated by a bioreactor. If we start to look at that scale, Certainly, I look at this and I see a pretty transformational change, perhaps decades. That's somewhere. It depends on the assumption of the contributing area per wetland, but something like 7,600 wetlands. Right now, we have about 72 that are specifically designed for this type of performance, and about 120,000 bioreactors. Some of the other scenarios call for 180, but even so, that's a lot of bioreactors. As I see this, one of the things that comes to mind, and you'll see the pictures from Rob, that's an awful lot of wood chips. And so even that may take time to grow wood for the bioreactors. Some of the estimates are every 10 to 20 years we might have to replace the wood chips in that bioreactor. So as we look at it, the strategy calls for this 41% reduction in nitrate. Just to kind of highlight again, like Sean talked about, we're not going to just do it with one practice. It's going to take a suite of practices, but that level of implementation is going to be very large for us to reach our goals. We need to get started on it, but we also need to set realistic expectations about just the time. As I think about this number, the number of wetlands and the number of bioreactors, we can just think about the time it might take to site, design, permit, and install that many wetlands. That's a fair bit of time. But on the positive, that could be a lot of small business opportunity in the state to put all those things in.